Okay. Okay, I hope the screen is visible as well. So, okay then, I think we have enough. Thank you. I think we have enough students now, so I think we can start. So welcome everyone to the problem solving session for the Introduction to Fluid Mechanics course, and this is Abhishek from IIT Kharagpur, and I will be one of the TAs to this course, aiding Professor Chakraborty in his lectures. And the specific, I would say, requirement or specific, very good evening, Devashish. So the specific purpose of these problem solving sessions is to uh, discuss some questions related to this first week's lectures, and help you to help you to understand the concept, as well as discuss questions that will be similar to the assignment questions that you will be asked to solve in the assignment 1 of this course. So that's the primary purpose, and we will do this every week on Tuesday 6 to 8. And I think that's the proper overview or of this session. So let's start. So as per my regular agenda, what I do is I briefly go through the concepts taught by Professor Chakraborty in his lectures. I'll just quickly briefly go through them. I will not dive deep into that. And if you have any doubt within those points, you can stop me anytime and ask. That's completely fine. Or you can unmute yourself and ask, or you can just type your doubts in the comment section, in the chat box. And then after discussing the concepts, we'll directly go to the questions. As you can see here, I have given some questions that are relevant to the first week's concepts, and then we can interact and try to solve those questions, and that will be it. Okay, sounds fine. Okay, okay, so let's start. So for the first week, we will be primarily dealing with the basic fundamentals of fluid mechanics. I am sure that Professor Chakraborty in his lectures have thoroughly discussed about the fundamental requirement of understanding fluid mechanics and how it is applicable in our day-to-day life. And I think that sets a very good motivation to study this course. Okay, so with that thing in mind, let's start our session. So, while discussing fluid mechanics, I guess Professor Chakraborty might have discussed about these two things: the microscopic approach and the macroscopic approach. Okay, so where microscopic approach basically means that we are looking into each and every fluid molecule and trying to understand the fluid mechanics system from the perspective of understanding the dynamics of each and every molecule in the system. Okay, and similarly in the macroscopic approach, we are now trying to understand the bulk behavior of the fluid mechanics system. Okay, for example, one of the parameters, or one of the variables or properties of a fluid mechanics system is pressure, which can be defined in the macroscopic perspective as the time average force per unit area. Okay, this is just a formal definition of pressure, and I guess Professor Chakraborty have discussed like how we are able to perceive this concept when we are dealing with fluid mechanics by the perspective of macroscopic approach. Okay. Sorry for that. Then, in line with these two approaches, there were two different methods, or I must say methods that were used to understand the fluid mechanics system. So, can anyone throw a bit of light onto that? Like for any fluid mechanics system, there were two approaches or methods through which we can understand or study fluid mechanics systems. So, can anyone please? Yes, exactly. Thank you, Daniel. Is a Lagrangian and Eulerian approach. Okay. So, Lagrangian approach is basically where we are following each and every fluid particle in the system and trying to understand what are the forces that are being applied on this each and every molecule, and then trying to find the sum of all these forces and then try to understand what are the total force that acts on that particular system. Okay. Similarly, in the Eulerian approach, rather than following each and every particle, we are more interested in a particular region of fluid flow system where we can focus our attention on a particular area and then try to understand what effects does the flow of fluid through that particular area has on the fluid flow system. So so as per your basic understanding that was discussed by Professor Chakraborty, that Lagrangian approach, though it may sound very interesting, and moreover it's much more accurate, I must say, than the Eulerian approach, because we are dealing a fluid mechanics system on a molecular basis. Okay, but as you can understand, this system itself comes with inherent drawbacks. The first and foremost being the cost. Like, following each and every particle in a particular fluid mechanics system is going to be extremely tedious and costly. Okay, and though it is very useful, and moreover people in fact undergo this kind of studies to understand the behavior of particles and motions in a fluid mechanics system, but it is a very costly, it's a very costly approach, very time consuming and very costly approach. Yes, of course, impossible in large scale scenario, exactly, thank you. That's why uh, the scientists or researchers have devised a new approach, that is an Eulerian approach of studying fluid mechanics system in a much more simplified manner that makes the study of this fluid mechanics system feasible. And that's why throughout this course we will be primarily focusing on this Eulerian approach of understanding fluid mechanics. Okay, so that's why we are discussing it right away, so that you can get an essence of what we are going to deal with in the rest of the course. Okay, and as you might have discussed, this particular region that we follow is the control volume, also known as the control volume. Okay, and when we discuss the Lagrangian approach, we are discussing a control system where we consider a particular fixed mass and identity of the system. Okay, so a fixed mass or identity, it means that, for example, if we consider a container. Okay, let me just use a, okay, so if you're considering a fluid mechanics system, like for example, let's say water inside a container. Okay, and say we are applying some force to swirl this. I think this drawing is quite small. Okay, so we are using some external force to swirl this fluid inside the container. Okay, so in this case the control system concept comes into picture, right? It becomes quite relevant, because here in this system, if we are going to understand the net force that acts on the fluid molecules, or the net force that is imparted on the surface of the container because of the motion of the fluid molecules, then we can apply this Lagrangian approach to study it, because here the mass of the system is conserved and the identity is fixed. The fluid molecules that were from the start of the rotation is remaining the same even after we are applying some force to rotate it. Okay, that's why the identity and mass are fixed. Now if you consider a scenario where we are dealing with a flow through a pipe, so that's why I will draw a particular cross section. Okay, cross section of pipe, and through which the flow occurs. Okay, so now if we consider this particular area, volume, say V, now when the flow occurs through this particular volume, even if the focused area remains constant, the fluid flow that occurs through this area changes continuously. Okay, I'm not saying the flow rate, but the fluid, the identity of fluid that passes through this region changes continuously. Okay, that's why the identity is not fixed. Even if the mass and the volume is fixed, but identity changes. That's why in that case we cannot apply Lagrangian approach to this particular control volume. Okay, because the identity is being changed. Like the fluid molecules, if you're following say 1, 2, 3 fluid molecules, and they are passing through this region, then in order to study these fluid molecules and its effects on the control's volume, we have to follow this fluid molecule throughout their life or throughout their trajectory. You have to follow it even after they have crossed this control volume, and that's not this does not come into relevance in the case of Eulerian approach. Okay, so once it goes throughout this control volume, we are not at all interested in the Eulerian approach perspective, but in the Lagrangian approach we will still be following these fluid molecules and trying to understand how even after passing through this region it has its effect on the control volume. Okay, so I hope this part is clear, or if there's any doubt I can repeat it. Is it clear? fixed mass identity in the Lagrangian approach. Sorry, I have a bit of cold, so I might do this again and again. I'm sorry for that. So is it clear? You can just write. Okay. Okay then, I think it's clear. So in that regard, while we're discussing about fluid molecules in our study, there is a non-dimensional parameter or non-dimensional number that is popularly discussed in the purview of fluid mechanics. That is the Knudsen number. Okay, so the Knudsen number by its definition is the ratio between the molecular mean free path over the characteristic length scale of the system. Okay, so although the definition of Knudsen number or this non-dimensional parameter seems quite simple, but an interesting thing to understand here is the term characteristic length scale. Okay, so depending on the system or the choice of the system, say if you're studying fluid mechanics system from the perspective of control volume or doing Eulerian approach to applying Eulerian approach to study this fluid mechanics system, then depending on the choice of your system, the characteristic length scale will also change. Okay, so for example, just saying, for example, if your system is a pipe, okay, as I already discussed here, let me use this diagram only. Say if your control system is or control volume is your pipe or this particular volume that you're considering within this pipe or duct, then the characteristic length or the characteristic length scale would be the diameter of this pipe. Okay, because it is the diameter of the pipe that is the most relevant length scale in understanding the flow through this particular choice of system. Okay, because in most of the cases these pipes are usually very long and have a very small or finite diameter. The pipe can be 100 meter in length and say only 10 centimeter or 5 centimeter in diameter. So the dynamics of the flow within this pipe is primarily governed by the diameter of the pipe, and that's how we define another non-dimensional parameter that is known as the Reynolds number, which we'll eventually see in the later part of this course. But that's how we define it. Okay, then now say if you are considering flow over a flat plate. Okay, a flat plate will basically be a rectangular shaped metallic plate or any plate made of any substance. That's completely fine. And then there is a flow occurring above this pipe. Okay, over this plate. Over this plate. Okay. In that case, in this scenario, since the diameter becomes irrelevant in this kind of geometry, then the characteristic length scale in this kind of flows is actually the length of the plate. Okay, so that's how we define characteristic length scale. It's just we will eventually discuss when we solve different kind of problems when we're discussing flow through pipes or defining Reynolds number. Then we will see how we can choose a characteristic length scale in a flow system. Okay, so I hope it is clear. Okay, so characteristic length scale is not a particular or a extremely unique value. It depends on the choice of the system. Okay, so I hope it is clear. Okay, then we discuss about the two extreme limits of this Knudsen number. So when the Knudsen number is very, very less than 1, then we consider that kind of system to be a densely packed system. Okay, and in these kind of scenarios, the continuum hypothesis is valid. Okay, so just one second. Yeah, the continuum hypothesis is valid. Okay, so I think I won't go through the continuum hypothesis definition because that was thoroughly discussed by Professor Chakraborty. Okay? But if you have any doubt, you can still ask if you want any clarification on that. Okay, and then the other limit is when the Knudsen number is much, much greater than 1. So in that case, it's a very, very rarefied system. Okay, and we cannot treat it as a continuous matter. Okay, so all the basics behind the Eulerian approach of studying this fluid mechanics, we will eventually see that it turns out to be a mathematical analysis of this kind of systems. And mathematical analysis will require that all the parameters or functions, say, that we are dealing with has to be continuous. Okay, that itself can, now you can correlate with the term continuum hypothesis. Okay, so for a mathematical operator or mathematical derivative to be considered on this kind of functions, the system or the domain that we are considering has to be continuous. Okay, sir, someone wants to ask something. Someone raised any hand, so I do not see. Okay, Divyanshu, who is it? I'm sorry, I'm not able to see someone raising hand. So you can either unmute yourself or you can just ask. It's fine. Or you can type in the chat box as well. It's completely fine. Okay. Okay. I'm not able to see who is particularly going to ask the question. So if that's the case, like, you can just ask him or her to type the question in the chat box. Then I can discuss it with the entire class. Okay. I think that's fine. Okay, Divyanshu, I think that would be the best way to deal with it. Okay. Yes, so in that scenario we need our function, the functions to be continuous, and thus the continuum hypothesis has to be valid to deal with this kind of fluid flow systems. But in the case where the Knudsen number is much greater than 1, then we cannot. Kanad has question. We cannot have okay, so what kind of properties are we going to observe in control volume? Okay, so I'm not actually understanding properties. Okay, okay, Karan, I will come to your question. Let me just complete my discussion, then I will come back to your question. I hope that's fine. Okay, I'll come back to your question. Okay. Yes, so as I was discussing, so if the Knudsen number is much greater than 1, okay, thank you, Karan. So if the Knudsen number is much greater than 1, then we cannot apply these governing equations or mathematical approach that we are using to understand this fluid mechanics system that we would have been able to do, given that the continuum hypothesis was still valid. Okay. So this is the scenario that we are not going to discuss in this course, but this is something that you need to know. So that's why Professor Chakraborty has thoroughly discussed about this, given some examples for that. I think you can go back to the lectures to understand those examples. But this is the basic understanding, like why the Knudsen number has to be much less than 1 for our analysis to be valid. Okay. So all the things that we are going to study are only valid when the Knudsen number is much less than 1. Okay. So that's what I wanted to emphasize upon. Okay. So coming back to Kanad's question, what kind of properties are we going to observe in the control volume? Okay, so I'm sorry, I'm not exactly understanding the gist of the question, but I will assume that you are trying to understand, like, what differentiates between a control volume and a control system approach. Okay, so again, let me just go back to this example. So you discuss our properties. Okay, so properties of a fluid mechanics system, for example, can be different parameters such as pressure, velocity, and if you are heating the system or you are dealing with temperature variation, then there is temperature. Okay, so these are the fundamental 3 parameters that we are going to study. Yeah, if you are only dealing with fluid flow systems, like if you are then mixing it with some other materials, then again the volume fraction of that particular material that we are mixing with the fluid comes into picture. So these are the properties that is relevant for both Eulerian and the Lagrangian approach. But the thing is, how you perceive these properties or how you calculate, evaluate these properties in the purview of Lagrangian or the Eulerian approach. Okay, so in the case of Lagrangian approach, say I will use the same example of pipe. Okay, so let us consider I am considering a flow through pipe. Okay, so I will zoom it a bit, then it will be much more relevant. In that case, say in the Lagrangian approach, okay, so say we are following these 3 particles. Okay, there are n number of particles, n can be even 1 million. Okay, so that's not the question. The thing is, how we are understanding it. Okay, so n can be 1 million. Okay, so we are considering 3 particles now, and say these 3 particles have this particular I will use different color, I guess, this particular trajectories that they follow because of fluid motion. Okay, if it is laminar, they will follow a straight line, but if it is turbulent, which is usually the more common case, it can follow any kind of trajectory. Okay, so say it is following this kind of path, this is following some different path, and doing this motion they can even collide with each other. Okay, so that's again a different thing to take into consideration. Okay, so they are following this path, colliding with the walls of the pipe, and then again flowing through the pipe. Okay, so the Lagrange approach would be to follow the paths of each and every molecule, fluid molecule in the system that we are considering, and system in this case would be the entire length of the pipe. Okay, 150 meter, if the pipe length is 150 meter, then 150 meter of pipe and the diameter of the fluid, and the diameter of the pipe would be the entire the volume of that particular pipe would be the entire system. Okay, so now if you're considering these 3 molecules, then these 3 molecules collide with each other, as you can see here. They can collide with each other and then collide with the walls of the surface, walls of the pipe. Okay, and because of this collision, because of the collision of these molecules on the surface of the walls, it will impart some force on the wall surface, right? And because of this this not only this particular molecule, but there will be n number of molecules that collide with the walls of the pipe, and then that itself would be now perceived as the sum of all these collisions to the surface of the pipe would be perceived as a total force that is being imparted by the fluid on the pipe. Okay, and this is what the Lagrangian approach is. And the properties that we are considering, for example, with velocity, one property is itself is the velocity, with what velocity these particles move in the pipe. Okay, because if we know the velocity, then we can know the the next point where the particle would be. For example, v would be u plus at, right? Simple equation of kinetic motion. Then if you know u and the acceleration and the time for which the particle is moving, then you can find the sorry, I'm extremely sorry, not this one. I'm confused. So say v is dy by dt, right? So if you integrate it using the simple say Euler's method, then y would be y naught plus v into t. Okay, then if you know the velocity in the initial position, that is 1 2 3 here, and the time for which it has traveled, then you can find the next point at which the particle would be, right? So this is the Lagrangian approach. So you know the position, then you can find the corresponding velocity, and there would be a particular equation that you will use to update the velocity as well, and that can be found out from the Navier-Stokes equation. That we'll eventually discuss how it is there. Okay, velocity field basically at each and every point of the control system. So this is how we are able to find the velocity, and using that you are able to find the force on the pipe, the pressure difference, and all these things. Okay, that's what happens in the Lagrangian approach. And similar properties or similar properties are relevant in the case of Eulerian approach as well. But in this case, rather than focusing on each and every particle, now we are interested in the bulk flow of the fluid. Okay, so now what we do is we consider the same geometry, that is the pipe, and now we consider a particular region. Rather than considering the entire each and every particle, now we are focusing on a particular region of the flow. Okay, so because of the flow because of this particular flow field through this particular control volume, there would be a particular force that would be imparted on this pipe. Okay, because of change of momentum. Okay, and that change of momentum that imparts a particular force on this pipe would be perceived as a total force that acts on this pipe. Okay, because of the effect of the bulk fluid flow through this pipe rather than the effect of each and every molecule. Okay, of course there's an approximation that we consider while evaluating these forces from the Eulerian approach, and if you are able to find the difference, you will find that this approach, the Lagrangian approach, is much more accurate than the Eulerian approach. But this Lagrangian approach comes with its own drawback, as discussed by as it was mentioned by Daniel, that it's very very costly. So just to tackle this high cost, and solve these problems in a cost effective manner, we use the Eulerian approach. Okay, so I hope this is clear, Kanat, or was this something else that you wanted to ask? Okay, I hope this is clear. You can just write on the comment chat box. Okay. I hope I was able to. Yes. Okay. Thank you. I hope I was able to clear it out for others as well. And but again, if you are not satisfied, if there's some more doubt, always go back to the lecture by Professor Chakraborty, or put your doubts in the discussion forum. Okay, in the course website. Okay. So then Professor Chakraborty might have discussed about the concept of traction vector. So can anybody give me? I have doubts about tensor and stress. Shall I wait to ask about it? Okay. So what I can do is I will briefly. of course I will not dive deep to each and every point of the discussion. So I will briefly go through the traction vector and its concepts. Okay. And maybe up till I can go up to the Cauchy's theorem. If it's not too long, I would like to go up to Cauchy's theorem, and then you can ask your doubt. Is that fine, Daniel? Because then your doubts will be relevant to other students as well. Okay, if they just might not have attended lectures or they're not clear about it, after discussion, then your doubts will become much more relevant. Okay. Okay then. Thank you for the understanding, Daniel. I'll just quickly go through these discussions, and then you can ask your doubt. I hope I will be able to clear it. Let's see. Okay. Yeah, sure. Thank you. So regarding the fluid and its deformation, Professor Chakraborty might have discussed that fluid, by its proper definition, is any substance that undergoes continuous deformation under the application of a very small shear force, okay, or any kind of small force. Okay, so it is a very formal definition of a fluid. Now when force comes into picture, and this force will apply on a particular region of fluid, so the relevance of traction vector obviously comes up, right? So I will not dive deep to the discussion by Professor Chakraborty. I'll try to go as fast as I could, so that I can invest more time on the assignment problems, or the this week's discussion problems. Okay, not the assignment problems that you have to solve yourself. Okay, sorry for that. Okay, so traction vector by its definition is defined as the force per unit area. Okay, but as it was discussed by Professor Chakraborty, this traction vector is unique in the sense that the value of this traction vector is not only dependent on the magnitude or direction of the force, but it's also dependent on the orientation of this area dA, where the orientation is quantified or comes into the picture through the normal vector of that particular area. Okay, this is given by this notation n. Okay, and this n denotes the unit normal vector in the outward direction of that particular area. So if this is the area dA, then n denotes the normal vector to this particular area. Okay. And the choice of n makes the traction vector unique. Okay, so if we change the n, that is the normal vector, which is related to your area dA, then the traction vector will also change. Okay, you will see how it happens. Okay, and the components of stress along a particular choice of n will give a unique traction vector. Okay, so this term I'll just see what stress means. You will eventually see what stress means, and you'll see how the choice of n will give a unique traction vector. Okay. So now let us consider this particular simplified diagram. So as Professor Chakraborty might have discussed, that why we are using this particular cuboidal shape, because see, this particular area or this particular shape is arbitrary. Okay, and to find a mathematical explanation or mathematical derivation through this particular arbitrary geometry is quite difficult. Okay, but in order to understand this dynamics of this traction vector, we use a simplified geometry, give some relevant approximations, and then try to find out the expression of these vectors and how it becomes quite relevant in the case of arbitrary shapes as well. Okay, and that's why we're using a very simplified approach. Okay, so now say we're considering this three-dimensional coordinate system, 3D coordinate system, and we're considering a particular cuboidal shape. Okay, this is given by this volume, and the x direction, this is the x direction, this is the y direction, and the z direction. And just to make it quite what to say, relevant for you for the later part of the course, we may denote it as, we can denote the coordinate directions as xi, where I denotes the particular direction. So xi equal to 1 will denote the x direction, I equal to 2 will denote the y direction, I equal to 3 will denote the z direction. Okay, it's the index notation as it comes to be properly I'm sorry I'm sorry for that. It comes to be more popularly known as. Okay. So here, if we consider this particular face of this cuboid, then this stress for this particular surface of the cuboid can be decomposed into three directions along the along the particular coordinate direction. Okay, so along the x direction we can write the stress as tau 1 1, along the y direction we can write the stress as tau 1 2, and then along the z direction we can write as tau 1 3. Okay, here there are two, as you can observe, there are two indices. Okay, 1 1, 1 2, and 1 3. So the first index denotes the direction normal of the surface. Okay, so it denotes the surface with respect to which the direction of the force is normal to. Okay, so you can see that this surface has a direction normal in the has a direction normal in the x1 direction. That's why we have the index as 1, and the direction of this force is along the x1 direction, so the index notation would be tau 1 1. Similarly, along the y direction you can see that it is written as tau 1 2. So this surface is along, the normal to this surface is along the x1 direction, so the first index will remain the same, but the second index denotes the direction of the force that is along the y direction, so it is tau 1 2. Similarly, in the z direction the surface remains the same, so normal to the surface will remain the same. So again the first index is the same, that is 1, but the second index would become 3 because it's along the z direction. Okay, so is this sign convention clear, or how the components of stress are divided for a particular phase, decomposed for a particular phase of the surface? Is it clear? Okay, thank you, Mayank. So I think as Professor Chakraborty have mentioned, you go through the sign convention, and I will also leave it as an exercise for you. I hope you understood this sign convention, or if not I can repeat it, like how in the opposite phase the direction changes. Is it clear, or should I repeat that? You can just say yes. Should I repeat it? The sign convention in the opposite phase? Okay, if there are no comments, then I will explain. Okay. Sure. Thank you, Kanat. So there was an exercise given by Professor Chakraborty to you that you should find the stress components for all these 6 surfaces. Okay, and it's actually a very good exercise, because from that you will get to know how are the stress components derived and the corresponding sign conventions. Okay, so as Kanat asked, let us discuss the opposite phase. Okay, so in the opposite phase you will see that again this surface, the direction normal to this surface would be in the negative x direction. Okay, so it will be in the negative x1 direction. Okay, so to make it as a positive, to make it in a positive sense, we will take the direction of the force such that it makes it in the opposite direction to tau 1 1. Okay, just so that the negative cancels out and gives as a positive term. Okay, that's why since direction normal is in the x1 direction. Okay, so that's itself is one negative sign included in the direction of the force. Now, to take into consideration the second index that will denote the direction of force, if we would have taken it in this direction, okay, then it would be something like tau minus tau 1 1, okay. But now if you are taking it in the direction of the opposite direction of the force, okay, then what happens is that we already had one negative I would say influence on the direction of this tensor because of the choice of the normal vector to that particular surface. And just to make it positive, in a positive sense, we take the force as well as the negative direction, so that the total contribution or total sign, the total product of these two signs would become a positive term. That's why it is chosen as in this particular direction, okay. It is tau 1 1 in that direction. So if we would have chosen tau 1 1 in this direction, then it would be minus tau 1 1. Okay, I will just write it here. If we have chosen tau 1 1 in this direction, in the positive x direction, then we should write it something like minus tau 1 1. Okay. Similarly, tau 1 2. Now I think it will be much more clear when we discuss tau 1 2. So in the case of tau 1 2, but won't it be confusing if you are using this for an algebra with the same? I'm just discussing but won't it be confusing if we are using this for an algebra with the same? I'm not getting it, like see, in most of the cases, say you will use, say, the components of this stress to find the force. Like let's say we are about to cancel these two tensors. Yeah, of course, this tau 1 1 and tau 1 1 in opposite direction will cancel out, right? They will cancel out. So the contributions that we will have would be from tau 1 2 and this stress components. Tau 1 2, I'm sorry, would be from these components, okay, and this will tend to give a rotation to this particular fluid element, okay. Yes, that's what I am saying. Say, you will see eventually when we discuss the how we find the Cauchy's theorem. We will see that these two components, this one and this one, would eventually cancel out. Why? Because, say, if you are trying to find a force, say it will be tau 1 1 into some area, okay, A1, and A1 in both the cases would be same, right? It is a cuboidal shape, so in the opposite direction, the area of the shape will be the same. So the net contribution of the force due to this particular stress component tau 1 1 would be the same, and it will cancel out, okay. But these two components, this tau 1 2 and tau 1 2, this tau 1 2 and tau 1 2, would try to create a rotation net. Exactly, the net force is 0 along the x1 direction because of these two stress components, this tau 1 1 in the right face and tau 1 in the left face. But these two stress components will try to create a rotational motion to this particular fluid element, okay, and that might not always be 0, but you will eventually see that because of the distribution of the stress components on this surface, they try to balance each other out so that there is no discernible rotation to this particular fluid element. You will see that, okay. But okay, Daniel, you can continue the question. Let's say it creates a curl in the z direction, then it won't be cancelling, okay. Let's say that it creates a curl in the z direction and it won't be cancelling. I'm not getting it. Curl in the z direction, so okay, fine, thank you. We can see the class for now, okay, sure, okay. Curl in the z direction, okay. Let's try to understand. I'll try to discuss it, okay. Thanks for the question. I think we will discuss more about it. I think he meant couple. Yeah, exactly. So as you will see that there is an assumption taken by Professor Chakraborty while deriving the Cauchy's theorem that there is no body couple in the fluid element. So that in that case, this becomes relevant. Otherwise, we have to again modify our equations accordingly, right? So Thanks. But the assumption is, yes, exactly. That's what I was thinking. Professor Chakraborty takes this assumption that body couple is zero, then only this Cauchy's theorem becomes relevant, right? Otherwise, it won't be relevant. So, does that clear a doubt, Daniel, or we want to discuss it a bit more? Of course, we can discuss it. Okay, Mayank, thanks. So, okay, so let's just proceed for the time being, and then after the class, I think we can. Okay, thanks. It makes sense. Okay, I think what I can do is I will dive a bit more regard onto that this week, and maybe if you join next week as well, we can. Yeah, we'll go into that, and next week when we come back to the class, I will just first clarify this particular question, and then we can start the rest of the topic. I hope that would be fine, Daniel. Okay. Okay. Thank you. Okay. Okay. So yes. So as I was discussing sign convention, okay. So the direction normal for this particular stress component would be in a negative direction. So there is one negative component. So in order to make the direction sense of this particular stress component to be positive, we need to choose direction such that it is opposite to the direction of the initial tau 1 2 that we chosen to be positive again. Okay. So it should be in a negative direction. So negative would give a positive sense to this particular stress component. Okay. Similarly, we can do for tau 1 3. Okay. So then again, this is we are discussing about stress and vectors. So the concept of tensor comes to the picture. Okay, so tensor, as discussed by Professor Chakraborty, is again a very involved mathematical topic. So for the scope of this course, we are not going to dive deep into it. It is a separate subject in mathematics called tensor analysis. So frankly speaking, I myself am not that expert in that, but just as a basic express stresses for 2D element like a square. Okay, we'll eventually go through that. I think we'll discuss this. Okay, Kanad, just wait for a while. I just want to go through the chronology of discussions, then we'll reach. Okay, thank you, Kanad. Okay, thank you so much. Do we use dot product or cross product here for tensor to normal? Uh, this actually is a dot product actually. If you're just discussing about it, this is actually a dot product, not a cross product. It is a dot product. Okay, then I'll just go through it and then we'll discuss. Okay. Okay, thank you, Divyanshu. So yeah, so as discussed by Chakraborty, tensor in relevance to this particular course can be limited to 2D. Of course, there can be 4D tensors in advanced fluid mechanics courses, but for the scope of this course, we are just limited to 2D tensors. And an example for 2D tensor, that is basically a mathematical term that has two indices, that requires two indices to be properly defined. For example, stress. Okay, because you saw that we need two indices to completely define the stress, and that's why the order of tensor is 2, because we need two free indices to define the tensor. So stress is an example of a 2D tensor. Similarly, vector, that is, for example, the velocity of a particular velocity in a particular direction can be defined as, say, v is v1 I cap plus v2 j cap plus v3 k cap, or in simple vector notation you can write as in index notation you can write as vi, when I will denote the particular component along the particular coordinate direction. Okay, so in that case the number of free indices in the case of velocity is 1, so vector is a first order tensor. Similarly, scalar, for example pressure or temperature, they are scalar quantities and they are not direction dependent, so scalars are zero order tensors. Okay, I think that's clear. So let's go through this example. So here Professor Chakraborty tries to find the relation between the traction vector and the stress components. Okay, so The relevance of traction vector comes to the picture when we are trying to understand the different kind of forces that acts on a particular fluid element. Okay, so if you are considering a fluid element in this tetrahedron shape given by this diagram, and as discovered by Professor Chakraborty, you should not take anything for what is anything that's universally true. Okay, so there might be some mathematicians who use different kinds of shapes to define a relationship between the stress components and the tensor vector. It's completely fine, but it's just a simple way that Professor Chakraborty has used to discuss the relationship between the stress components and the traction vector. Okay, so it's not universal, it's just that we have used to define it for our simplicity. Okay, so let's consider this particular tetrahedron shape. Okay, and say the surface S1 is AOB, so AOB would be surface S1, then AOC would be surface S3, this surface, and OBC would be the surface S2, and ABC, let us say it is a surface S. Okay, this surface is given by surface S. Okay, and the normal vector to this surface S is given by n cap, this is n1 I cap plus n2 j cap, sorry, plus n3 k cap. This is 3D, right? n3 k cap. Okay, so in this particular fluid element, there can be two types of forces that acts on this particular fluid element. First is a surface force, and then there is the body force. Okay, so examples of surface force can be pressure and shear stresses or normal stresses. Stress component, basically stresses that acts on the fluid element, can be considered as surface forces. Okay, or the force because of the stresses can be considered as surface force. And body force, example of body force is gravity or electromagnetic forces. These kind of forces are known as body forces. Okay, but surface force by its very definition, it means that it acts on the surface or acts along the surface of the fluid element. And body force, it means that it acts in throughout the volume of the fluid element. Okay, it will have its implication throughout the volume of the fluid element. Okay, so that's what the body force means, and because of their very definition, we have to treat them differently. Okay, and the relevance of traction vector now comes into picture when we are trying to find the surface force. Why? Because see, when we're discussing surface, then we are discussing pressure, which is a scalar quantity, and the stress components, which is a second order tensor. Unable to see screen presentation. Okay, but is no one able to see, or it shows that the presentation is, the screen is, I'm still presenting. So are others able to see the screen? Please someone say yes or no, otherwise I have to reconnect. Okay, Kanad is able to see it. Okay, Divyanshu, are you able to see now? Or thanks Nitish. So Divyanshu, are you able to see now, or is it still not visible? Can you just confirm? Otherwise I will just reconnect. I'm not able to see. Okay. So I will try to reconnect. I think that's what I can do right now. Okay, so I'll try to reconnect Divyanshu. Let's see if you're able to see it now. Okay, Divyanshu. Okay, we can also try to rejoin. Okay. So is the screen visible for others? One yes would be. Oh, thanks, Mayank. Okay, then it's visible. I think Divyanshu can reconnect. Thank you, Joravar. Okay. Okay. So as I was discussing, now since we're discussing surface forces, as I already mentioned, here we saw that there's pressure and stress components. Okay. So the stress components by its very definition is a 2D tensor. Okay. So, but surface force is a vector. So now we have to find a way to convert or modify the stress components in the form of vectors that gives us the surface force. Okay, because surface force is a vector quantity and stress is a second order tensor, so we need to find a way to find the contribution of the stress components in the form of vectors, and that becomes relevant because we saw that stress is a 2D tensor, right? I and J. see stress is denoted as tau ij. Okay, there are two free indices now. So thus it will have, if it's a 3D coordinate system, so I can have 3 components, j can have 3 components, so 3 cross 3, it will have total 9 components. But force is a vector quantity, so if I varies, this has 3 components, then it will have only 3 components. So we need to find a way to find the contribution of these other 3 components along the direction of a particular I, that will give us the force along that particular direction. Okay, so that's where the concept of traction vector becomes relevant. Okay, so to understand that, we just find we try to do a force balance for this particular tetrahedron shaped fluid element. Okay, and these surfaces S1, S2 and S3 can be denoted as SN1, SN2 and SN3, basically showing the component or the projection of that particular surface S along the n1 direction. Okay, along the direction of the normal vector, the component normal vector along the x direction. Okay, that's why S1 is SN1, S2 is SN2 and S3 is SN3. So elaborate about SN1, SN2. Yeah, so you can see that, say this surface is S. Okay, this surface is S, then the projection of this surface, or if you are trying to visualize this surface, try to see the component of the surface that falls along this particular plane or in the direction of n1, that would be in this direction. Okay, so that would basically be this surface, right? So we can say that this surface can be given by S into n1. Okay, is it clear? Another phase. Okay, so like again same thing. So if you are trying to say along the y direction, okay, direction normal to this y direction. Oh, I'm sorry. Okay, I'm sorry for that. I think I created confusion. Okay, I'm sorry for that. Say along first, let's start with x direction. Okay, so x direction, in the x direction, the surface perpendicular to this x direction is this surface. Am I correct? It is perpendicular to the x direction. So direction normal perpendicular to the surface that has a direction normal along the direction of the x component is this surface, right? So normal vector is along the x direction. Am I correct? Okay, so the component or the projection of this surface S along the direction of the x direction would be this surface, right? S1, right? So from that we can find from there we can find the relationship between this surface S1 and S. Okay, similarly, if you are trying to find the direction normal to the y surface, right, the surface perpendicular to this y coordinate would be this surface that we named as S2. So the projection of the surface capital S on this particular plane would be given by S is equal to S2 is equal to S into N2, right? Okay, so it is coming to the concept of projection. So let us try to discuss it. How can I, just 1 second. Okay, so the projection of, say, this surface S. Okay, so let us try to n would be So mm, say you want to find the component of the surface S along this particular direction, n2 direction. Okay, so S can be denoted as S1 I cap plus S2 J cap plus S3 K cap. Okay, just then S2 would be S into N2. Okay, so okay, just give me 1 second. I'm trying to find it. How to denote the, sorry. Okay, so it can be I'm just trying to correlate it, so I hope it makes sense. Okay, so say S, I'm trying to find an area vector. Okay, so let it be S I cap plus S J cap plus S K cap. Okay, then along, say I'm saying that S2 would be S dot N cap. It would be, sorry, N2 V S N2. Okay, yeah, that's what I have written here. So I'm just trying to ensure that whether, sorry, this is what I've written here. I'm just trying to ensure whether this presentation of the surface S is correct or not, but this is how we are able to obtain it, like finding the component or the magnitude of the surface S along the, say, particular normal direction. So in this case I've taken as N2, so it would be, so S along the y direction would the vector along the y direction would basically be n, sorry, to j cap. Okay, basically j cap. So it will give this particular value. Okay, so I'm just trying to correlate whether it is correct or not, but I think that's how we are able to obtain it. Okay, so it might not be clear properly, but I think I'll try to look into it and try to find a more robust mathematical conclusion, like how we are able to obtain it. So would that be okay, Kana? Sorry for the lack of clarification, but would it be okay? I figured it out. Okay, can you just share the what you have figured out in the? Can I? Yeah, of course, please. you can tell me. I can just try to write it down, then it would be quite relevant to other students as well. You can tell me. Yeah, you can speak. Yeah, please. I'm unable. You are unable to hear me. So wait. Are others able to hear Kannad? Yeah, I think others are not also not able to hear. Can you just write it? I think it not be a big derivation. Can you just write it in the chat box? There might be some issues in the mic or the internet connection. So can you write it in the? Oh, you can hear. Oh, Kannad. Then I'm sorry, I'm not able to actually hear you. So can you just write it down in the chat box? If we take dot, yeah, we took dot product, right? I took dot product only, but along the y direction. So Kannad, you can just write on the chat this chat box, then we can continue. Okay, protected area. Yeah, that's what I was mentioned. Okay, it is a dot product of S and N. Okay, so S dot N would give S1 and 1. Yeah, that's what I've written here. So is it the one? I am just underlining. I am just noting it here. Then we have to treat it as like that only. Right? All the components along. Sorry, the would be the same. That would make sense. Okay. Okay, then I think this is the part that I've initially written was correct. So this one was, sorry, this one was, it makes sense. Then S2 becomes SN2. That's how we can find out. So okay, then I think we can proceed further. Okay. If Kannad rejoins, then he can clarify it further. But don't worry, I will try to put this clarification in the next class as well, or otherwise in the discussion forum. Okay. Sorry for the confusion, other students to other students as well. Let us try to continue. Okay. Okay. So S1 is SN1, S2 is SN2, and S3 is SN3. Okay. Then with this simplification, okay, and the body forces along the x direction is given by the volume of this tetrahedron, half into S into H, into the body force per unit mass, that is B1 along the x1 direction. Okay, then just trying to do the force balance along the x direction. Okay, so I could not type due to internet issue. Yes, Kanad, please continue. You can write your answer there. I'm really also intrigued to find out the answer. You can continue to write. Okay, I'll just keep on discussing this part. Then I'll look into the chat box. Okay, please continue to write the answer. I would really like to see it. Okay. Okay. Then just doing a force balance along the x direction. Uh, Here we are taking the contribution of these stress components along the x direction only. Okay, so that's what it is shown here. So just for the sake of saving time, I'm not going to tell how you have done it, because you can just find it if you have properly understood the sign convention of the stress components in this particular scenario. Okay, so keeping that in mind, then we do the force balance along the x direction or the x1 direction to get that minus tau 11 s1 minus tau 21 s2 minus tau 31 s3 plus tau 1n is a traction vector along the surface S, plus 1 by 3 s into h into rho into b1 is equal to 1 by 3 s into h into rho into a1. Okay, considering the fluid particle or fluid molecule can be in motion. Okay, so okay, should not break. We should not break the components of S as S1, S2, etc. We should just break it based on just unit vectors. Then take the dot product. Oh, sorry, Ketan, I guess he raised the hand. Ketan, yeah, Ketan, you've raised your hand. Si cap S equal to Si cap, J cap, Sk cap. Yeah, that's what I have written here actually, but I'm not entirely sure whether this is correct or not. Okay, that's why I was, because this part is clear and I know you need to take a dot product, but I'm just not able to clarify it in a better way. Okay, that's why I was being confused, but I'm just seeing Kannad's explanation and we can. Okay, so Kannad, we should not break the components of S as S1. Yeah, we have, that's what I have done here. Taking the dot product with n will give the correct answer. So actually that's what exactly I have done here, but I'm not I'm just being not sure whether this is correct or not. That's why I was confused a bit. Okay, so that's what the issue, but still, like, that's how that, because that's the only way mathematically you can arrive in this conclusion, arrive to this conclusion. But to be conceptually correct part, that's the part I was being a bit confused. Okay, that's why I'm not sure about this derivation, but that's how mathematically you can approach it, arrive into. That's what I've exactly done here. Okay, so okay, then just for the sake of saving time, of course got it, sir. Yeah, exactly, for sake of saving time, let us just skip this part. This is a very crucial part. So what I will do is, if any one of you join the next week session, I will discuss this beforehand just as a continuation for this week's session, and then start the next week's discussion. Okay, then I think that's fine. Sorry to all the students for the confusion that I'm creating in this part. Mathematically this is correct, but conceptually how you arrive into it, that's what I am a bit confused. Okay, so okay, then let's just go through it once. Okay, so one way to think that is, like, say, I'm just trying to give a last try. So for example, if this is the surface S, okay, and it has a particular, if you consider this surface S as a vector, okay, then we can write it as S as S I cap plus S J cap plus S K cap. Okay, given that the orientation of the surface may be in any particular direction, so the surface can be treated, because surface may not be even, right, may not be completely even all the time. So surface can be of any arbitrary shape, assuming that this surface has different components having the same area. So I can write it as S I cap plus S J cap plus S K cap, given that S is a magnitude of the surface along this particular coordinate direction. Okay, now what I want to do is, what I actually want to hit here was that I want to find the component of this surface S along a particular normal direction. Okay, so I want to find the component of S along, say, the n2 normal or normal along the y direction. Okay, then what I can do is n2 j cap is itself a vector. Okay, considering that these two components are 0, then n2 j cap is itself a vector along the y direction. Okay, then we take the dot product of these two to find S2 as the direction or the component of the surface along the y direction as S dot n2. Then we get S2S Sn2, which basically gives the component of the surface along the y direction. Okay. Okay, so I think that's what I want to discuss. So Kanad has written something more. In this case, we have three separate normal vector. So n1, n2, n3. Yeah, but S is unique in this sense. Hence, it should not be broken into S1, S2. Okay, we are not breaking it, right? So we're not breaking it. It's that one. Okay, so I think Kanad, you can give your explanation, and thank you. You're adding so much to the discussion here. So you can continue this discussion. Just write it if there's something more left here. You can write it in the chat box, and then we can discuss. Okay, so I want to complete up to the pressure part. That was thank you for being patient. Yeah, that's my job here. Okay, thank you for being so interactive. For other students as well, I'm sorry. S1 is just a representation to write Sn1. Yeah, that's what I wanted to say. But thank you once again, Mayank. So thank you, Kanad, Mayank, and all the students to make it so interactive. So just for saving time, I would like to complete the up to the pressure part. Then I would like to discuss some questions, and then we can continue this discussion. Okay. Thanks for the doubts. I'm sorry if I'm not able to clear it properly. I will try to clarify it in the next class in the best way possible. Okay. So let's just try to complete these derivations, and then which is already done in Professor Chakraborty, but I'm just trying to reiterate it so that it is clear. But thanks for putting the doubts. It's helpful for me as well. Okay, then yeah, then from derivation, so if we again do the same substitution like S1 as Sn1, S2 as Sn2, and S3 as Sn3, then we get we substitute it in this expression to get, we can then cancel out S from all these expressions to get minus tau 11 n1 minus tau 21 n2 minus tau 31 n3 plus tau t1 n plus 1 by 3 h into rho into b1 is equal to 1 by 3 into h into rho into a1. Okay, so as a simplification, if you are considering the free element to be very very small, then the height of the tetrahedron would be approach 0, then these two terms become negligible. Then you can consider this is the approximation 1 by 3 part. No, so that's actually the volume of the expression for the volume of the tetrahedron. Okay, 1 by 3 into the surface area into the perpendicular height. That, like how to show it. So if this is this height h. Okay. Okay then. So then if h is too small, then this both of this expression will be equivalent to 0. Like you can just consider to be negligible. Then from this we can finally write the traction vector or the component of traction vector along the x direction as tau 11 n1 plus tau 21 n2 plus tau 31 n3. Okay, or in a generalized form as discovered by Professor Chakraborty, this can be written as tau I n, because if you substitute 1 by 2, then all these ones have to be has to be replaced by 2. Okay, so to generalize this expression, we can write it as tau I n is equal to summation of j from 1 to 3 as tau ji into nj. Okay, so j would vary from 1 to 3. Okay, so it will basically be tau I n would be tau, sorry, I'll just write it with a okay, so tau I n would be tau j1 n1 plus tau j2 n2 plus tau j3 n3. So here you can see that this j, oh I'm sorry, I did a mistake here. J is the repeating index here, summation is over j, so it would be tau 1i n1 plus tau 2i n2 plus tau 3i n3. Okay, so you can see that I is the free index here because it's only repeated once, not repeated once, it's only it only comes up in this expression for one time, so it is a free index. In j, since it comes up twice in this expression, so it is the repeating index. Okay, since it's repeating twice in the expression, and that's why in the Einstein's index notation form, this repeating index basically denotes a summation in the index notation. Okay, so tau in can also be written as tau ji into nj, where it inherently means that there is a summation over this repeating index j. Okay, that's what's known as the Einstein's index notation. Okay, the repeating index indicates a summation. So this tau, the traction vector is a vector, so tau I represents the I is equal to 1, 2, 3. So now what we can do is we can represent this traction vector in the form of, in the matrix form. To find the components of the traction vector, we can represent it in a matrix form. So in order to do that, we can write it as T1 n, T2 n, T3 n would be equal to tau 1 1, tau 2 1, tau 3 1, and this matrix form multiplied by the normal vector n1, n2, n3. Okay, and it's a matrix multiplication, so multiplication will have to be done in this manner. So this is a way to completely define the traction vector, and these particular elements denote the components of the traction vector. Okay, and there's a very important statement that the second order tensor maps a vector on a vector. So as I mentioned, so the second order tensor, that is the stress in this case, maps the traction vector with this normal vector, okay, along the direction of the normal vector. Okay, because we were interested to find the contribution of the stress along a particular direction, because we are interested in surface forces, so we wanted that we want the stress in the form of forces, or the components of stress that will give us a force, which is a vector. So we use a second order tensor, which is the stress tensor, to find this force along the particular normal direction. Okay, this is n1, n2, n3. Okay, basically it will mean that tau 1n is the net force, traction force, or the surface force along the n1 direction. Okay. So I think one of the doubts was regarding the stress along a particular, I don't know, one of you asked about okay, one of the students, I'm sorry I forgot the name, one of the students asked about the say a square, like what's the stress distribution over a square. Okay, so considering the same sign convention, so if we consider this along the x direction and this along the y direction, okay, then the surface normal along the x direction would be in this direction, so the first index would be 1 for all the stress components along this surface, and the second index would be direction of the force. So tau, it would be tau 1 1, so the second index is 1 because it's along the x direction. Similarly, for the second stress component, it is along the y direction, it would be tau 1 2 because it's along the surface that is perpendicular to x1, okay, or x direction. Similarly, in this surface, it would be the surface normal is along the y direction, so the first index would be 2 because it is y is again x2, right? So first index would be 2, you can see it's written here. The force along this direction is along the x direction, but it's along the surface that is has a surface normal along the y direction, so it is the second index would be 1, and for the component along the y direction would be tau 2 2, so 2 would be denotes the surface normal direction, that is along the y direction, and the direction of the force is along the or the stress component is along the y direction, so it is tau 22. Okay. Similarly, here again the surface normal is along the negative x direction here. So there is one negative sense that we need to counteract to make this in the positive direction. So we take the force or the stress component along the negative x direction, so that we can take into account the negativity that was induced in this particular term because of the choice of the normal vector. Okay. Similarly here, so the normal vector is along the negative x direction, so we need to choose the direction of the force stress component along the y direction and negative direction, so that this negative gives a positive sense to this particular stress component. Similarly, finally, in the final surface, so here along the negative y, the surface normal is along the negative y direction, and the component of force along the has to be chosen in such a way that it gives this a positive sense, so the direction of force is along the negative y direction. Similarly, in the last component is the surface normal is along the negative y direction, so tau 21 is chosen in a way that the direction of the force is along the negative x direction, so that this negative cancels out and gives a positive sense to this particular stress component. So the student that asked about the stress distribution on a 2D plane, I hope this is clear. Okay. Okay. So as one was I think one of the students. Okay, thank you, Kana. So I think it was Daniel that was discussing about the curl part. Okay, so body couple part. Okay, so assumption here is that the net we are similar to the previous case where we were conserving a linear momentum. Basically, we are doing a force balance. So now we are doing the conservation of angular momentum. So the expression for the conservation of the angular momentum is given by summation of the force along moment along the z-axis, that is outside of this plane. So outside of this plane in this direction is Iz into alpha, where Iz is the moment of inertia along the z-axis. Okay. Again, these normal components, that is tau 11 and tau 22, would cancel because they are in the opposite direction, having the same surface area. So the net force because of these stress components are in the opposite direction, so they cancel out. Okay, so they are not contributing in generating any moment along the z-axis. Okay, but these components tau 12 and tau 21, they have a tendency to generate a rotational component along this z-axis. Okay, so if we consider this as length delta x and this as delta y, this entire length is delta y, then the moment with respect to the z-axis because of this stress tau 12, because you can see that these two stresses create a couple that try to rotate this element in the counterclockwise direction, and tau 21 tends to rotate this fluid element in the clockwise direction. Okay, these two will try to rotate this in the clockwise direction. So the moment because of this stress component tau 12 would be tau 12 into the area delta y, right, and the distance between these two couples, it is delta x. Okay, minus, because the direction sense is in the negative direction, so it will be tau 21 into delta x, that is the surface, into delta y, that is the distance between these two couples, would be equal to the moment of inertia along this particular z-axis. So it's given by rho into delta x into delta y into 1, this volume, into the delta x square plus delta y square 12, the moment of inertia, into the angular momentum. Now if we consider this fluid element to be very, very small, this delta x and delta y tends to 0, then we can write tau 12 is equal to tau 21, and in general we see that tau ij is equal to tau ji, given that there is no, as I mentioned, there is no body couple in this particular fluid element. Okay, so that's what I think was being discussed by I think that's thoroughly discussed by Professor Chakraborty, and he emphasized on this assumption that there has to be no body couple for this expression to be valid. Okay, so I think it is clear till now. And Daniel, does this discussion clear your doubt regarding the curl component that we are discussing? the algebra part. Like it's something that is difficult to what to say, understand through the question, but is it what that we were emphasizing upon, or it was something else, or is it something else that I'm not able to perceive? Okay, so okay, then there is Cauchy's theorem. So this relationship between the stress, the attraction factor and the stress components is also known as Cauchy's theorem. So this term is known as Cauchy's theorem, and here you can represent, you can replace tau j as also as tau ij, because in the absence of body couple, the stress tensor is a symmetric tensor. Okay, and that's why we generally say in the case of fluid mechanics, or generally in the case of mechanics as well, that the stress tensor is a symmetric tensor, but there has to be a very robust assumption that there's no body couple in that particular element. Okay, in general that's not there, but special scenario there might be there, but in general there's no body couple in such scenarios. That's why we can say that the stress tensor is also a symmetric tensor. Okay, and that's why I will just write it. I think that will make a much more sense. Say tau ij. Say if I'm writing for a Cartesian coordinate system, that is x, y, z coordinate system, then we can write it as tau xx, tau xy, tau xz, tau yx, tau yy, tau yz. Finally, tau zx, tau zy, tau zz. So Professor Chakraborty told that in this kind of scenarios there are 6 independent variables when you're considering stress components. So the 6 independent variables would be 1, 2, sorry, let me just mark it. 1, 2, 3, 4, 5 and 6. So these would be the 6 independent stress components, and this would be equal to this one because of the symmetric nature of the stress component. This would be equal to this one because of the symmetry, and this would be equal to this one. And that's why he mentioned that usually there are 6 variables, because the stress tensor is symmetric, and we're able to write the Cauchy's theorem in this manner. Okay then, so let's now finally come into the discussion of pressure. Okay, so again I will not dive deep into the diagrams. It's quite self-explanatory and it was thoroughly discussed. I will just go to the derivation. Again, if there's any doubt in the discussion, you can ask. Otherwise, I'll just continue. So, if you are considering the force balance on this particular field element, that is considered to be in motion because you're considering the acceleration term. Okay, so considering the force balance along the x direction, we can write minus px into delta y, this along the x direction. So one I have not written it here. Pn, I'm sorry, just write the components. So this is theta. So Pn into delta L sine theta plus half into x into y into rho bx, that is the body force along the x direction, would be equal to half into delta x and delta y into rho ax. Okay, the mass into the acceleration, okay, along the x direction. Now considering that, okay, please explain this portion. Okay, which part? Which part? Body force numerically. So numerically, body force in general, when we are discussing it in the context of fluid mechanics, so we generally consider it as, say, if bx is the let me just write it as capital B is bx I cap plus by j cap plus bz k cap. Okay, so what we generally do is we consider that bx, the small bx, is actually uh, the body force along the x direction divided by the mass. Okay, so we consider the small bx term as an intensive property multiple of which other terms. Okay, okay, sure, thank you. So the small bx is actually the intensive property of the fluid flow, which is the ratio of the component of the body force along the x direction divided by mass. Okay, or say if you are considering the weight of the body. Okay, what's weight, if we're considering it as a vector, then we can then consider it, say, as say wx I cap plus wy j cap. Not weight, I'm just saying the body force because of gravity. Okay, so let me just write it as capital G. That would make a more sense for gravity. Okay, so let me just write it as capital G is g x I cap plus g y j cap plus g z k cap. Okay, so usually in the case of, if we are considering gravity as the body force, okay, because gravity would act throughout the volume of the body, like, right? So in the case of gravity, these two components become irrelevant. One second. Okay, sorry for the disturbance. Okay, so in the case of gravity, these two components become irrelevant. Why? Because we know that the gravity always acts along the z direction. Okay, if you're considering it in that way. So say, of course it depends on choice of the coordinate system. So if I'm saying that it's x, y and z, then the gravity would act along negative z direction. So this term becomes relevant, and this is what is perceived as the mass, not mass, weight of the body, or this is equal to m into g. Okay, mass times the component of gravity along the z direction. Okay, or otherwise if the orientation of the gravity is in such a way that it has components along the other directions, if the choice of coordinate system results in a way that the gravity can be dissociated into its components, then it becomes quite relevant. Okay, then these two components also become relevant. But for simplified terms, when we are mentioning a coordinate system that has the gravity aligned to one of its particular coordinate directions, then the other two components become irrelevant. Then the only component that becomes relevant is the weight of the body. Okay. Is it clear till now? Divyanshu? Kanan, is it clear till now? The body force discussion? I'm sorry. Okay. So explain the pressure part. Okay, I will come to that as well. Okay. Okay then. So just wait 1 minute. My Apple pencil is charging. So just kindly wait 1 minute. Okay. Okay. So the pressure part. How would I show? So okay. So here, this. So as I mentioned that, yes, it's okay. Okay, thanks, Divyanshu. So as I mentioned, this fluid element may be in motion. Okay, and that is a very crucial statement. As Professor Chakraborty might have discussed, that the pressure is some entity that that what to what can, that, I, that plays a crucial role while determining the dynamics of fluid molecules or fluid system when it is static. Okay, but the thing again is that the application of this body force might result in the motion of the fluid itself because of gravity. Okay? The gravity also might have effect on the fluid molecule. For example, if it is static, right, if the fluid system is kept stationary and it's being heated, then the buoyancy effects have its own implications on the fluid flow. Okay, the bulk, there is no bulk motion in the fluid element, but there are internal motions occurring within the system. So in that case, the body force comes to the picture. Okay, and the fluid may be in motion even if the entire system is at rest. Okay, so considering the scenario that we are just doing a simple force balance, that is summation of fx is equal to max. Okay, and you may ask that if the fluid is in motion, as Professor Chakraborty had mentioned, if fluid is in motion, there would be deformation in the fluid surface because of shear forces, right? And you can ask that then because of that there has to be the contributions on the surface of the fluid because of the shear stresses, right? That is also relevant, but right now I'm just focusing on a scenario that what role the pressure has on the dynamics of this stationary fluid element. Okay, so that's what I was trying to discuss. Okay, you will eventually see that the stress when we thoroughly discuss the later part of the course, you will see that the stress can be divided into two parts. Stress is tau ij hydrostatic plus tau ij deviatoric. Okay, it's a bit advanced for now, but the stress can be dissociated into two components, and pressure will come in this compartment because it is the stress that acts on the fluid element when it is at rest, and when it is in motion, when it is in motion, then the other stress component also comes into picture. This is the deviatoric part. So the total stress would be the force due to the pressure or the hydrostatic stress plus the force due to the deviatoric stress part. Okay, so this is, I would say, it is a general case in the sense when the fluid is at rest, but this case is still valid when the fluid is in motion. So the effects of pressure would be still relevant when this expression would be still relevant in the case when the fluid is in motion, but this case becomes the generalized case when the fluid is at rest. Okay, so that's why we are taking the case when it is in motion, but these derivations become the generalized or the fundamental solutions when the fluid is at rest. Okay, so let us just go through it. Discuss the pressure part as well. So in this case the pressure part is only becoming relevant because we are considering initially that it is at rest. Okay, so there can be the stress components as well when it is in motion, but we are disregarding that part because we are only focusing the effects of pressure on the fluid element. Okay, then considering the the force balance along the x direction. So along the x direction, the pressure would act always. It's a okay, but actually meant the expression p sine theta part. Okay, I will come into that. Okay, so along the x direction, so it is the pressure it's a very inherent property of pressure that pressure always acts opposite to the direction normal of the surface. Okay, thus we will see that the direction normal of these surfaces would inherently be in the outward direction, but pressure always acts in the opposite direction to the surface. So basically it tries to apply a compressive force on the fluid element. Okay, that's a property of the pressure. Okay, so along the x direction we have px into delta y into 1, so we can just disregard 1 for now. 1 is basically the width along this particular direction, so we can disregard it for simplification of the calculations. So it is minus px into delta y. This is the length of the this area. Okay. Then along the y direction, it is y direction. It will have no contribution in the x direction, so we can disregard this part. But this will have contribution, right? Because of this normal stress, normal pressure Pn. So it would be Pn into L and the component of force along the x direction would be Pn into L into sine theta, right? This component along this direction would be Pn L into 1 into sine theta, right? Because it is not the pressure that we dissociate, but it is the force. The force would be Pn into delta L, and the component of this force along the x direction would be Pn into delta L into sine theta, right? But we can again see that delta L sine theta is delta y, correct? So we can replace delta L sine theta y x, we will multiply with x, right? We'll see. Sorry, y, yeah, because delta L sine theta is y, right? Delta L, sorry, delta L sine theta would be y, right? Delta y in the x direction, yeah, because this is the surface area, right? Got it. Okay, thank you, Kanan. Okay, so I think others also got it. So delta L sine theta is delta y, so replace delta L sine theta by y. So we'll have these parts I have already discussed. So if delta x and delta y tends to 0, then from here we can replace y from all the terms. So we will have with this expression, and if delta x also tends to 0, then we will have px is equal to pn. Similarly, by force balance along the y direction, we will have pn equal to py, and in that case we will have pn in the generalized case we will have pn is equal to px into py. Okay, so pressure can again be considered in two forms. It has two ways in which we can perceive pressure. First is the mechanical pressure, that is the sum of all the normal components of stress divided by 3, the negative part of sum of all the components divided by 3 normal stress components. Okay, these are normal stress components divided by 3. So it will be minus tau 11 plus tau 22 plus tau 33 divided by 3. Okay, this is a mechanical pressure. Okay, and as I was discussing with deviatory stress, so the stress that deviates from the hydrostatic part. And then there is the thermodynamic pressure obtained by the equation of state. Okay, so if you are considering ideal gas, so sorry, P would be equal to rho RT. So this is the equation of state. Okay, so from here also you can find the pressure for a particular system, and in general this mechanical pressure is equal to thermodynamic pressure. Okay, but as mentioned by Professor Chakraborty, that in some cases the system undergoes rapid changes and the system does not get enough time to adjust to these rapid changes. In such cases, mechanical pressure is not equal to thermodynamic pressure. Okay, it's a very rare scenario where I can say the response time of the system is larger than the changes that are occurring in the system. So in that scenarios, the mechanical pressure may not be equal to thermodynamic pressure. Okay, so that's the special case. So because in most of the scenarios, this mechanical pressure is equal to the thermodynamic pressure, but there might be scenarios, as mentioned by Professor Chakraborty in this example, that where the mechanical pressure may not be equal to the thermodynamic pressure. Okay, so I think that's all from the discussion part. If you have any doubt, I think you can ask after the question Q&A part. So let us go to the discussion. Okay, so in these questions, I think it's quite similar to the ones that you will be asked in the assignment for this week, but let's just go through it. You can just tell me the answers one by one. Okay, so if tau ij represents a component of stress tensor acting on a fluid element, which among the following assumption is made for arriving the relation tau ij is equal to tau ji? Okay, for one it is C. Okay, that's correct, because we have thoroughly discussed how it is relevant, so it is correct. So others, is it clear why it is C? We have discussed it thoroughly. We will go to the gone through the derivations, so I think it should not be that challenging, but let's see. Okay. Next question is, state true or false. The Knudsen number is defined as the ratio of the characteristic length scale of the system to the molecular characteristic length scale. Is it true or false? So it's false. Okay. So because it is actually the inverse, because Knudsen number is Kn is equal to lambda by L, where lambda is the molecular mean free path. Okay, and L is the characteristic length scale. Okay. Which of the following statement is or are incorrect? Okay, is or are incorrect. A Lagrangian approach deals with the tracking of individual fluid particles. Euler's approach deals with tracking of fluid within a specific region in space. The Euler's approach deals with tracking of individual fluid particles. So question number 3, can you tell the answer? What would be the answer? 3 is C, so that's again correct. So I encourage others also to reply. It is good. C, thanks Aghas, thank you. Thanks Kanat. So 3 is C, that's correct. Let me just number the questions. So okay. So question number 4 is, it's a bit again a bit more involved question. Which of the below options provide a correct explanation for a flow augmentation on rough hydrophobic surface? Okay, so there can be more than one correct answers. So basically asking why the flow can slip over rough surfaces in some scenarios. Okay, so the options are: liquid particles get trapped on rough surfaces of the channel. The roughness of the and hydrophobicity together lead to a formation of a layer of tiny bubbles which cushion the roughness of the channel. The flow velocity is generally greatly reduced due to the hydrophobicity of the channel surface, or none of these. A and B are correct. Okay. So let me look into others. Can you tell? B. Okay. So actually both are correct. One is like, okay, one can also be considered to be correct, but the more correct answer or correct, because if I am asked, then I will give both answers correct. But like if other faculties who are more, what to say, want to be more thorough with the concept, then option B would be more appropriate one, because here it mentions that it's because since the surface is hydrophobic. Okay, since the surface is hydrophobic, then it inherently tells that the surface would not want the fluid particles to be get trapped on the rough surface of the channels. Okay, even if there are protrusions coming out of the surface, so it will not want the particles to get trapped on the surface of the on this rough surface. So what actually happens is that instead of liquid particles being trapped, it actually traps bubbles. Bubbles are formed because of the hydrophobic nature of the surface, and these bubbles indeed get trapped in the rough protrusions that comes out of the surface, and these bubbles form a layer which tend to the slippery nature or the flow being effectively slip on the surface of the rough surface. Okay, and the effect of the protrusions on the flow is not felt because of the layer or the cushions of the cushion of the bubbles that are formed because of the bubbles being trapped on the protrusions. Okay, so if I was told, I will say both are correct, because this concept also important, but instead of liquid particles it should actually be bubbles. Okay, because bubbles makes more sense because of the hydrophobic nature of the surface. Okay, so the next question is, which among the following is or are incorrect statements? Okay, the Cauchy's theorem is basically a statement of linear momentum conservation. The Cauchy's theorem is valid only in the presence of a body coupled on the fluid element. Cauchy's theorem expresses a traction vector on any arbitrary plane in terms of corresponding stress tensor components, or D, all of the above. So question number 5, what would be the answer? Can you tell? Incorrect. Which are incorrect? A and B. Okay. So Divyanshu says C. It's incorrect. Divyanshu, can you recheck the statements again? Kanat says A is incorrect. Like is or are incorrect. There can be more than two incorrect. Okay, I think Divyanshu understood the assignment now. So, Kanat, can you just see, like we discussed, that is valid only in the is valid in the absence of body couples. So, I think B is also incorrect. A is definitely incorrect because for a symmetric nature we need the angular momentum conservation as well. Yeah, so B is also incorrect. Okay, so A and B both are incorrect. Okay, thank you. So let us go to the next question. It's very simple. We just now saw which of the following relationship is true for defining mechanical pressure of a system. So all the expressions seem quite similar, but one of them is correct. It's just the indices that we need to understand. So can you tell which one is correct? Yeah. So Shanawaz says it's D. Shanawaz, I'm sorry if I'm pronouncing it incorrectly. Shanawaz say it's D. Others, can you also contribute? B is also incorrect, sir. D. Okay. Yeah. So Kanad and no idea. Daniel, is it question number 6? Daniel? Yes. Oh, so this is what it is, a mechanical pressure. So we just discussed it in the last part of the discussion. Okay. The expression for it. So it's quite understandable if you just missed out. No issues. So we just discussed it here. The mechanical pressure is equal to the negative of the sum of the or the average of the normal stress components. Okay. It's minus of tau 11 plus tau 22 plus tau 33. These are normal stress components divided by 3. Okay. So similar to that, you can just check the indices that tau in the Cartesian coordinate it will be xx, yy and zz. So tau xx, tau yy, tau zz represent the normal stress components. Okay. It's quite understandable. So and option D is correct. Okay. So question number 7 and 8. This is question number 7 and 8. This is common image for both the questions. So let me zoom out a bit. Let us consider a small triangular fluid element as shown in the figure 1 below. Here Px, Py and Pn are the pressure acting on these three surfaces. I think the diagram is self-explanatory. We have just discussed it now. It was in the opposite sense, but the derivations are quite relevant. No, it's fine. It's fine, Daniel. No issues. It's fine. No problem. Okay. So question number 7 is which among the following is the correct statement? A. Px equal to Pn only if there is no body force along the x direction. Px equal to Pn even if there is a body force along the x direction. C. Px equal to Py not equal to Pn for all cases. And D. So can you tell which answer is correct? We just derived this. Okay. So we Shanawaz and Aghas says, Divyanshu says C. Correct statement. B. Okay. So actually the correct answer is B. So if we look back in the derivations, we obtained these expressions that Px equal to Pn and Py equal to Pn, and I told that this is a generalized case. Okay. So here you can consider if the fluid is at rest, then it is the more I will say the generalized solution for this scenario. But even if it is motion, these expressions are still valid because we can dissociate the stress into the hydrostatic and the deviatoric part. So the hydrostatic part will contribute from the pressure, and the deviatoric will be contributed from the stress part. So this expression is still valid even if the fluid is in motion because the pressure will still exist. Okay. Only the case is only that when the fluid is in motion, then the shear stress component will also come into picture. So we need to add some additional forces to this diagram to take into account the deformation of the fluid element. but pressure will still persist. Okay, and that's why this is a generalized case. Deviatory is the stress components that basically the shear stress components. Basically, the stress components that deviate from the hydrostatic part. That's why it is called deviatoric. Okay, okay, okay. So this is a more generalized solution. So this is valid for uh, all the cases. Okay. So option B would be correct. Okay. Question number 8 is, sorry, Px equal to Py equal to Pn holds true for both moving as well as static fluid element. State true or false. I think I just discussed it right now. Yeah, it's true. I just discussed it. So this is valid for both moving and stationary fluid element. So most of the times students get confused that this relation, this also basically known as a Pascal's law. If you just go back to your elementary science books, they discuss about the Pascal's law, that pressure is transmitted equally in all directions. So this is valid for this expression. This Px equal to Py equal to Pn is valid for both static and fluid moving fluid element. Okay, but sometimes student gets confused that this relation is only valid for your static cases. It's not the case. Okay, it's valid for both static and moving fluid elements. Okay. And the last question is question number 9. Which of the following statements is or are correct? Okay, we have won the correct answers. A second order tensor is a transformation tool that maps a vector on another vector. A second order tensor is a transformation tool that maps a first order tensor to another first order tensor. Pressure may be considered as a tensor of order 0, and D, all of the above. So can you tell which is the correct answer? D. Okay, so others, Senavas say D, others Kanad and Agas. Okay, then since all of you are saying it's actually D, so I mentioned that a second order tensor is used to map a first order tensor to another first order tensor, and this is their statement. Vector is a first order tensor, so second order tensor can be used to map a vector to a vector. That's again correct. Pressure is a scalar quantity, so it is a tensor of order 0, as I already mentioned. So the correct answer is all of the above. Okay, so that's all for today from my end, and time is also up, it seems. So Daniel, I think you had some questions. So just for the since the time is already up, if you don't mind, can you please put your doubt in discussion forum? Like if it's not clear till now, the body couple part and the curl part that you're discussing, you can put in discussion forum, and I'll look into it and discuss it in the next class. Would that be fine, Daniel? Okay then, so thank you everyone. Thank you for this interactive session. First week it was quite interactive. I didn't expect that, but let's all meet in the next week. I will thoroughly discuss that normal vector part as well. I think it's more or less properly understood, but still I will try to find a more robust expression for that. Use speaker next time. You're audible to us, but we're not audible to you. Okay. I will try to look into that issue. Okay, I'm sorry for that. I would like to see I think there's some issue with my laptop, but I will just look into it. Okay, thank you then. Thank you Kanat. I'm actually sorry that I was a bit confusing in the normal vector part, but I will try to clarify it in the next class. Okay, thank you then. Let's all meet in the next week session. Okay, thank you. Okay then.